Here, and this is the Stanford Math Tournament Number Theory section problem number 7. Here's the view of this problem. Let a be the positive integer that satisfies the equation, this equation, and what is the remainder when a is divided by 17? Okay, so maybe the first order of business here would be to combine this such that we have only one fraction and the denominator is 30 factorial. And the numerator will be something ugly and we can just try to reduce to mod 17. So let's go ahead and do that. We know that 1 is 30 factorial over 30 factorial. For 2, we want to exclude the 2 in the numerator. So we have 30 times 29. So times 3 times 1 over 30 factorial. That way the 2, there's no 2 in the numerator, so it goes to the denominator and everything else cancels out. Similarly for 3, for 2 over 3, we'd want the 2 out front, and then we'll multiply 30, 29, all the way until 4 times 2 times 1. 4 times 2 times 1. Divide this by 30 factorial. And we keep on going until we reach the final term, which is 29. We want a 30 in the denominator, so let's just multiply by 29 factorial, so 29, 28, 2 times 1 over 30, right? 30 factorial, 30 factorial. Yeah, okay. So now what we want to do is we want to reduce the numerator modulo 17. We can do this piece by piece. We know that 30 factorial will contain a 17 in its expansion, so this is just 0. And furthermore, any numerator that has a 17 in its incomplete factorial expansion will reduce to 0 upon modulo 17. So the only term we really have to care about is when we have 16 over 17, where we have no 17 in the numerator, because that's the only term that's not going to be 0 mod 17. Alright, so now let's just do the exact same process. We have the 16 out in the front. To get to 30 factorial in the denominator, we can multiply it by 30, 29, and then we'll stop at 18, continue from 16, and go until 2 times 1. And then we'll divide this by 30 factorial. And then now we need to reduce the numerator modulo 17. Okay, so modulo 17, we know that 16, the outermost 16, that's just -1 mod 17. And then we can maybe from the left, from the right, we can go to the left, and then we can group the first as 16 factorial, which by Wilson's theorem, we know that this is -1 mod 17. And then Wilson's theorem just states that for any prime, we have the prime minus 1 factorial is congruent to the -1 mod the prime. Okay, and then now we can maybe pick up over here. We have 18, which is 1 in mod 17, 19, which is 2 in mod 17, and then all the way until 29, which is 12 in mod 17, and 30, which is 13 in mod 17. Okay, so I want to kind of simplify this, which is 13 factorial modulo 17. And the best way to do that is kind of try to get it to Wilson's formula. So let's denote this as capital A, and then we have that capital A times 14 times 15 times 16 is just 16 factorial, which by Wilson's theorem we know is -1 mod 17. So what we now want to do is let's reduce each of these. 14 is -3, 15 is -2, and 16 is -1. So this combined is -6, which is 11. So 11a is congruent to -1 mod 17. So now, in order to isolate a, we want to multiply 11 by its inverse so that this reduces to 1 mod 17. And to do that, we'll just note that 11 inverse is congruent to, I believe, 14 modulo 17. and that's simply because 11 times 14 is 154, which is one more than a multiple of 17. It's one more than 153, and 153 is 17 times 9. Great. So now we know that we can multiply both sides by 14 to get A is congruent to, okay, times 14. A is congruent to 3 modulo 17. Okay, and then we know that we have these two, which will just combine to be 1 mod 17. And when we multiply by 3 by 1, we get 3. So this is our final answer, and we're done.